My name is Oisin Boydell, and I'm from CEDAR, which is the Centre for Applied Data Analytics Research, and that's at University College Dublin. And I'm going to talk about our paper, which we call Deep Learning at the Shallow End, Malware Classification for Non-Domain Experts. So to give a bit of context, so malware analysis and detection and classification faces a number of challenges, and these are related to the huge volume and variation of malware and data that is present. It's very dynamic, so malware is constantly changing, it's constantly adapting. There's definitely a cat and mouse between malware creators and developers and tools and approaches to prevent that and analyze that. Also, it requires very deep domain expertise. So the techniques, the tools, the expertise that is required in order to analyze it and to understand what it's doing and the different methodologies for measuring what it does and how it acts is it's very specialized. This is also very time consuming. So for example, running malware in a sandbox environment, measuring its different impact and pulling out different features and behaviors of what that's actually doing, that takes a long time. And this makes it very hard to scale. So as there's more and more different types of malware, the issue is becoming more difficult to scale to these large volumes. So these traditional approaches require very specialist tools, computational resources. So we're talking things like virtual machines, specialized sandbox environments that need to be configured, isolated networks where the monitoring of network communications can be done, which is completely separated from broader connected networks, for example. And the time as well. So malware often needs to be executed in real time for analysis when you want to determine its impact on the underlying hardware, or network traffic, and so on. And it needs to be run in real time as it would be executed in a real environment. And then the expertise around this it takes a huge amount of expertise. And this diagram on the right shows a number of different approaches. It might be a bit hard to read in this resolution. A number of different approaches and techniques that are commonly used. So there's things like in dynamic analysis, you're building a virtual machine, you're testing using malware sandbox, you're monitoring the activity, you're using monitoring processes, you're detecting DNS activity. Then you're looking at things like extracting strings from static malware, you're analyzing the linked libraries and disassembly and so on. And all this takes a huge amount of time. It's hard to do. There's a lot of expertise and computational resources to do this. Machine learning in malware analysis is a new-ish area. So currently there's a lot of interest and ongoing research around using machine learning for malware analysis. There's a number of good surveys on this. So for example, in 2017, this survey on usage of machine learning techniques for malware analysis. And there's another from 2014 there. And in our paper, we provide a sort of high-level review of machine learning techniques in this area. So what machine learning can do is it's been used to automate and also improve the accuracy of many malware analysis tasks, and particularly the last speaker was talking about an interesting approach in this field. And it's particularly been applied to malware classification. So that is, once you have a number of different types or classes of malware, to automatically infer for new examples what class that this particular piece of malware belongs to. And just to give an overview of the machine learning and a bit of context for our work. So this is a typical workflow and how a machine learning task operates. So you start with a labeled training set. So in this case, these could be different examples of malware, which are each labeled to a different malware class. These are then, machine learning algorithm then trains over these examples and produces a trained model. This trained model then has learned the patterns and the different expressions of these different classes of malware. So then when you get a new example, an unknown class, you can query the model and give a prediction of which is the correct malware class for that model. So this obviously depends on the scope of your training data set and the classes that it contains in it, and the capabilities of your machine learning algorithm and so on. But this diagram kind of misses a crucial step here, and it's a sort of simplified view. So in the majority of traditional machine learning algorithms, what's required is this feature engineering and extraction step. So traditional machine learning algorithms, they can't operate directly on the raw data. So in this case, the raw binary malware files. They need to operate on higher level features. But the extraction of these features is a very manually intensive work. It requires a lot of expertise and understanding what that data means and what kind of features are useful for the classification task. So now we've gone to a scenario where we need both the domain expertise to understand malware, to disassemble it, to run it in different sandbox environments, to measure the activity of it, to pull out these higher level features. And in addition to that, we need the machine learning expertise as well. So there's a lot more complexity to do machine learning for this type of malware analysis. And as I said, as I mentioned, the generation of these features is still very manual. And some of these typical kinds of features that are used in malware machine learning classification is static features such as processor instructions, strings and other static resources that are contained in the code, library imports and system API calls. And this can be done from statically viewing the malware files. So, for example, using maybe disassembly tools, etc. Then there's also dynamic features. So these could be dynamic system API calls, also interactions with other resources such as memory and storage as the malware is actually running. So the previous speaker, their approach was very much focusing on this interaction with the memory. Then there's the network communications. But these are still the same kind of features and the same kind of tasks that traditional malware classification relies on, which, as I said, it needs a huge amount of domain expertise. So to introduce deep learning. So what deep learning is, it's a type of machine learning, and it's based on artificial neural networks. It's called deep learning as there's many levels and layers of these artificial neural networks, which allows these models to simulate very complex relationships between the data and the output. So they're able to model very complex functions. However, a key feature of deep learning is its ability to operate on very low-level raw data representations. So this is a diagram here that I borrowed to kind of represent this. So, for example, with a traditional machine learning approach on the top, we see in this example that this could be, for example, to classify whether an image contains a car or not. So we have the input, which is an image, for example. Then there's this stage of feature extraction, which requires manual knowledge, manual effort to extract the various features maybe in that image that the algorithm can then operate on. This goes into the classification model to learn that model, and then this can provide predictions as to whether or not an image contains a car or not in this example. However, if we contrast this to deep learning, the deep learning model is able to do this feature extraction part and the classification part all as a single operation, and it learns the features automatically from the data that correspond to the output and the function that it's trying to learn. We can look into that just in a little bit more detail here. So we see on the left-hand side typical rule-based systems where you have hand-designed program, domain experts hand-designing the various rules in the system. Going to classic machine learning where we still have hand-designed features, but in this case the model learns the mapping from these features to the output. However, on the right-hand side here, we have representation learning, and this includes deep learning on the right-hand side, where the input, we can give the models the raw input. They can infer the simple features. They can build up additional layers of more abstract features from these simple features, and also learn the mapping from these to the output. And deep learning, because of this ability and its ability to map and learn very complex associations, it's rapidly achieved state-of-the-art performance across a broad range of application areas. And there's quite a lot of publicity, it's quite well known. So, for example, in image analytics and machine vision, we have huge successes in object detection and image classification. It's completely transformed that field. We've seen it in things like playing sort of human games. So, for example, Go. A number of years ago, Go was considered a game that might be quite a number of years off before computers would be able to beat the top human players. But this has happened in the last year recently with AlphaGo. And we've also seen applications in the medical domain. For example, there's an image there analysing cancer from medical imagery. So this is based back on the image analysis, and also Google Translation of the services are very much based on this. So deep learning has a lot of different applications. So we've applied this deep learning approach over the raw data for malware classification. So we're looking at building these models on the static raw malware executable data. So just the raw static data. And what we have here is, this is just a visualization of a couple of examples of malware files where we've visualized in the raw malware bytecode in terms of grayscale, and we've put these into a 2D representation. So this just shows that between different malware examples there is a lot of patterns, a lot of information in that, even looking at it from this context. So we can see there's a lot of information here, and this is the kind of raw data that machine learning and particularly deep learning algorithms can really harness and take advantage of. And this is a data-driven approach, so the idea is to allow the model itself, the deep learning model, to learn the features from the raw data itself. So just back to the motivation, so what are we doing this for? Well, there's no deep malware domain expertise required. So we're running the model directly on the raw bytecode of the malware files. There's no sandbox environments, no disassembly, no need to manually identify and extract the features requiring that expertise to know what to look for. It's easily adaptable to new types of malware and class types, so it just requires label training data. And the speed of it as well, so there's no need to actually run or disassemble the code. This whole feature extraction process isn't required. And the classification is purely based on the static raw bytecode. But the question is, well, how can an approach that's based purely on this static bytecode and essentially ignores a lot of this human malware domain knowledge and work that's been done in determining what features work well for machine learning based malware classification, how could this be any good? Well, in our evaluation, we tried 3 different model architectures. So convolutional neural networks, which are commonly used for image, machine vision and image analysis. So these work on very small localized regions in the data to find localized patterns. We also evaluated a model which had convolutional neural network layers followed by unidirectional long short-term memory. So what this is able to do is to find longer distance association between these underlying patterns that the CNN architecture can infer, and to find longer distance associations across the malware file. And we also tried a third model which used a bidirectional LSTM layer on top of the CNN. The data set we used was from Kaggle, so there was the Kaggle Microsoft Malware Classification Challenge back in 2015. The URL's there, it's a public data set. So this was over 400 gigabytes when it was uncompressed. It contains malware examples in 9 different labeled classes, and there's over 10,000 malware files as raw bytecode, which have the labels in the training set. And then there's a test set without labels. So for our work, we were focusing on the training set as the original challenge closed in April 2015. So we had to use the examples that had the labels provided. So there was some required data pre-processing. So although our approach is very much designed to work on the raw static malware bytecode, we did need to do some pre-processing. But this is easily automated, and it doesn't require a particular analysis on per different types of classes, for example. So what you see here is a histogram of the file size of the malware examples in the data set. And as we can see, there's a range of sizes ranging from quite small right up to quite large file sizes. Now, one of the restrictions of the types of deep learning architectures that we're using is that all the examples for training and for classification need to be a common size. So what we did is we used OpenCV, which is an image analytics library, to compress each sample down to a length or up to a length of 10,000 bytes. So this is a lossy compression in itself. So it's again using quite a lot of information from the raw original file, the raw data. But we used this image compression technique because this type of compression is designed to preserve the patterns, designed to preserve the information in the data as they're used on image data. And another advantage of this as well is that to train the deep learning model on the original size of data would be very intensive in terms of computational resources. So by reducing the size of the training examples, it just makes it more feasible for training. There's also a class imbalance in the data set. So as you can see here, the 9 different classes of malware, and there's a huge variation in the number of examples, but some of those have a very small number. And this can cause problems in the learning context. So we applied 2 approaches to this. So the first approach, we simply preserve this class imbalance, so we keep the data as it was in our training. And the second approach, we use resampling and oversampling to balance this representation in the training data. So to show the results, so we used 5-fold cross-validation on the data set, and you can see here that the different accuracies for the different architectures we used and the 2 sampling approaches for each architecture. So the best performing accuracy and the DFRWS score, which is a measure of accuracy that's balanced by this class imbalance to give a more accurate depiction of that. Well, we can see the top performing model that we had was the CNN with the bidirectional LSTM and using the rebalanced data set for training, where we got 98.2% accuracy. So this sounds pretty good. But what we need to know is what's the context of these results. So how do these results compare to other approaches? So 2 similar approaches that are related are from this paper, first one from novel feature extraction, selection, and fusion for effective malware family classification. So in this work, they used traditional machine learning approaches and algorithms, and they also used features engineered from the disassembled binaries and from other more traditional feature extraction processes. But they also combined this with classic visual image analysis. So those visualizations of the data that I showed previously, they did a similar thing on the data, and they used classic image analytics, image classification approaches, and features from that using XGBoost. And they were able to obtain 95.5% accuracy using the exact same 5-fold cross-validation approach that we did. So we were able to beat that at least with 98.2% using our approach. Another related approach was using convolutional neural networks similar to our approach. So what they did is they just used the basic convolutional neural network on that raw binary data. They didn't use the compression. They used a much more complex model with many more variables in it as well, so it was less practical from a training and with real-world practical use. So they got they measured their accuracy using log loss, through the Kaggle data set. There's more information in the paper about these particular metrics. So they got a public score of log loss of 0.11, private score of 0.13, whereas when we evaluated our approach using the exact same methodology, we were able to get a log loss much less for both the public and private segments of the data. So there's more information about that in the paper. So our approach was able to better these similar approaches that we can show that in the context of how our results compare. Also, what was interesting to us is the practical runtime considerations, because we were very much trying to simplify and enable the malware classification and malware analysis to be more practically used. So this shows the training time. So our most complex model, we have a training time of just under 2 hours, and this is on some quite specialized hardware, a number of GPUs, which can speed up the deep learning training time. But to put this in context, this is an offline process. This training only needs to be done once. It can be easily updated as new examples arrive, which doesn't take the full training time. And this is done offline, so this can be done. It's not required when you're classifying new malware examples. Whereas if we're classifying a single new binary file, it only takes on average 20 milliseconds, and that's on a pretty standard machine using CPU. So this shows that this kind of approach can be used in kind of live, online, near real-time context, where you might be classifying this malware or a stream of files as it's seen, for example, in a real-life context. So just to summarize our approach, so our approach, it doesn't require deep domain knowledge of malware. It doesn't require time, tools, and resources for the complex feature extraction, which is sort of commonly the methodology for malware analysis, and particularly machine learning for malware analysis. Classifying new instances is very fast, so it's practical in online, live, and near real-time applications. And it's also very scalable to new identified malware types, so you just need the labeled examples, and the model can be incrementally trained on those. And we've shown it can achieve very high accuracy as well. So just some conclusions. So we'd like to evaluate on other data sets, and we're particularly interested in binary malicious benign classification tasks. So this could be used in the context of a malware filter and detection application that's running in real time. We'd like to explore the capability to identify and report like the similarity between malware classes and variants. So to use this trained model as an analysis approach to analyze how different classes of malware relate to each other. And we think there's some interest there. And we'd like to apply it to the task of determining the type of binary packing used, so the packing approach. So we've had some discussions with the National Cyber Security Centre in Ireland, and they actually proposed this as a task which they found took quite a lot of manual work to do and slowed up their kind of workflows. So to provide it for that. And my background isn't in forensics. I'm coming from a machine learning background, so I'd be very interested to talk to people about potentially other applications that might arise that we are not aware of. So finally, if anyone has any questions, the code from this paper is like that URL, so people can rerun these examples, and the data is publicly available from Kaggle. Thanks. Sorry, can you say that?
The question was, in your opinion, why do you believe malware classification as a problem is needed?
Yeah, I think it can work in a number of contexts. So one is for the analysis of malware, so understanding how different classes maybe relate to each other. I can also see that it can be used in terms of tools to filter and block malware, so in determining which different types of malware is being encountered, and to do that very quickly. And also in terms of more the binary sort of benign versus malicious versus benign, having that as a prediction on new ones seen quite good.
Right, so you were using this data set from Kaggle, which was already labeled. Do you know what labels were created there? Like why did those labels assigned to those
Yeah, so, well, I mean, I'm not sure of the details of how that data set is generated, and I'm sure that data set it represents quite a small view on malware. There's only 9 labels there. I presume that's created from Microsoft malware analysis teams. Yeah, I do agree it's a fairly restricted data set. We'd like to try our approach on a much more expansive broad data set.
My question was slightly different. So you use like static analysis with a static approach, so you don't run the file itself, run by itself. But then all the labels that we get 91 families, they are assigned based on the behavior, based on what the malware does, how it does, what it does. And so when we choose how do you then interpret the results? So you're getting like not 100% accuracy, but 95 or 96% accuracy. So how will you then interpret why you lost those 4%? Since you also use data compression to reduce the size of the volume, you lost some information, and how to relate your business application to the labels, to the way your design.
Yeah, well, I mean, I suppose firstly, the results, I think, show that a lot of the information of what class that a particular bit of malware belongs to, at least in this data set, is in that raw binary, the static raw binary, and that can be learned from this particular types of deep learning models. So that information is there to an extent, and that can be leveraged. That seems to be what the results show for us. And that's including this kind of compression, which loses a bit of the information. I presume, to achieve higher accuracy where that bit's missing, we go up to much higher accuracy. I mean, I presume one interpretation would be that those compression techniques, you're going to lose some information by doing that. So maybe that missing information is leading to that. But I mean, I have to say that we were quite surprised by the results that we were able to get using just this raw data. That's something for us to do, actually, to interpret a bit more, because there's ways to look into the deep learning model to analyze what those features that it learned are, and to maybe relate those back to the original file. So that'd be an interesting area to understand, and that's something maybe that would be good to work with someone with some more in-depth expertise of how malware works, because that's not our background, and we don't have the full expertise to do that.
I'm curious of how or why this approach would work for packed malware, because I would assume the malware is packed or otherwise encrypted. Most of the information about the features, I would think it would be completely opposite. Is that not
yeah. So we're not sure in the data set. I don't know whether those examples were all packed, or maybe we're assuming they're all. But we'd like to apply the approach for the second correlation task of predicting or inferring which type of packing approach would use for various binaries. So the model then learning the features of the different packing approaches to be able to tell very quickly from just an example file to say it's likely to be packed using this.
I would assume that would be successful just based off the unpacking stuff, if nothing else. That even if the data is completely random, there still needs to be some code to unpack that data. But that's not going to give you information about whether this is a worm or ransomware.
Yeah, so that might be a two-step process if we're dealing with data that is, you definitely know it's not unpacked in different cases. So firstly, to infer the packing mechanism, unpack that, and work on it.
That makes a lot of sense.
Did you test for a correlation between file size and malware class?
No, we haven't done that. So we were working with the data that was compressed down to these this specific length, in our case 10,000 bytes. So there was a couple of reasons that we did that. Firstly, the deep learning models and architecture we're using required that all the data similar case. Now there's ways around that, but we didn't want to add in that complexity. And secondly, it just enabled our approach to be more scalable, because that specific size and number of bytes that we chose was something that we could feasibly build models on. So yeah, we didn't look into analysis further of those sizes. We just used kind of went from this standardized size.
Because I think this is really cool work. I think this is the first one where I've seen deep learning applied. But I'm concerned about those two possible spurious correlations, which is the packing. Because if each of these malware classes used a different packer, then your results could be due to the packer.
Mm-hmm. Yeah.
That's similarly, it is correlated with file size. And I'm not familiar with the loss compression algorithm that OpenCV uses, but that may be part of what the success is due to.
Mm-hmm.
That compression.
Yeah, no, I understand. Those
That's
concerns.
what might be, since so many of your samples, and it's hard to say because your diagram starts with 0, so surely none of them are 0 weights. So it's kind of unclear. 10,000 is pretty low in your histogram there. But it'd be also interesting to look at, what if you just look at the first 10,000 bytes of each of those? Because you can still get most of your samples there. So I think
Sure. Yeah. So well, we did actually try an approach where we just truncated the first 10,000 bytes of the file, and yeah, it wasn't as successful as this approach. And then what we did for the files that were smaller, because there's a number that were smaller than that size, we truncated, or we put zeros on the rest, and it wasn't as successful as when we used this approach. But I agree that there's lots of scope, I think, for further testing of this approach on different kinds of data sets and just further analysis.
Any further questions?